We are going to talk about applications of open loop op-amp circuits today. So we kind of set the ground rules in our last class meeting for how we expect things to kind of behave. And by that specifically, I mean talking about, or how we talked about saturation, distortion, and linear range. So what I'm going to introduce today first is what's called a non-inverting comparator. And this is essentially going to be almost exactly the circuit that we analyzed at the end of our last class meeting. Okay. So let's say that we have something akin to this. So here is my basic op amp, choosing to put my non-inverting terminal on top. So on the non-inverting input side of things, we are going to apply some input voltage. So I'm going to choose to draw this input voltage Vn of t like this, where we're just applying the signal to this terminal. So just to be clear here, this is simply a shorthand notation for putting a voltage source there, where we're assuming that the positive polarity terminal of our source is actually connected to the pin, and the negative polarity terminal of that source is connected to ground. So this is just drawing it in a way that's going to be a little bit more compact. On the inverting input pin, we are going to put what is called our reference voltage. This is usually going to be some DC voltage. Then we're going to take our output voltage here at the output pin. Usually, because this is a real circuit, we would probably have some sort of loading resistor right here. And so I'm just going to put this as RL, and I'm just going to make a note here. Typically speaking, these load resistors are going to be in the kilo-ohm range of resistances, okay? I'm also going to make a note of our positive supply voltage VCC plus and our negative supply voltage VCC minus, because at the end of our last class meeting, we learned that since the op amp can't have an output that is larger in magnitude than our supply voltages, we need to pay attention to what those are, because in this open loop configuration, we are effectively going to be outputting those supply voltages almost the entire time, because we saw that the linear range of an open loop op amp was so incredibly small. Okay. So this is our circuit. Okay. So if we were to represent this particular circuit using the practical op amp model, we would have something akin to this. So let me start here. So here's my input resistance. This is going to be my differential voltage VD, making this guy my non-inverting input terminal, and this guy is my inverting input terminal. On this side of things, I would have that dependent source, where here I will have my open loop gain, AVOL, multiplied by my differential voltage VD. Here is my output resistance, R out. My ground bus down here. And for what it's worth now, I'm going to put that load resistor across these terminals. So here is RL. Our output voltage is then going to be the voltage drop measured across that load resistance RL. We have a reference voltage source placed between the inverting input node and ground. So that's going to be this guy right here, VREF. Let me draw that less crappily. And we're going to have our input signal between the non-inverting input terminal and ground, like so. All right. So what my ultimate goal here for us to do is essentially, I want us to plot the output voltage of this guy as a function of the input voltage. We're going to do that up here on the kind of top right corner of this thing. So this x-axis will be V in, and the y-axis will be V out. Let's give ourselves some constraints for this guy, okay? So let's say that our input voltage will range from -5 volts to +5 volts. Let's say that our reference voltage will be exactly 2 volts. Let's say that our open loop voltage gain is going to be very large, so we'll just do 10 to the 5 volts per volts like we did last time. Our input resistance will be 1 mega ohm like last time, and our output resistance will be, let's say, 25 ohms like last time. And then finally, our load resistance, we'll say, is a 10 kilo ohm resistor. Really, what I'm trying to get out of this very specifically is that our load resistance RL is much, much greater than our output resistance R out, so that for that simple output side voltage divider network, effectively all of whatever AOL times VD is should be occurring across the load resistor. The voltage drop across that 25 ohm R out should be extraordinarily small. In fact, so small that we should be able to neglect it. Okay. Okay, so I'm going to make a quick note on here that this point right here represents 2 volts for our reference voltage, because that's where we should see things start to change. So let's start out at essentially one of the extremes. If Vn So let's put Vn over here on the left-hand side and V out over here on the right-hand side. So let's start with Vn is equal to -5 volts. Okay. If Vn were -5 volts, what would our differential voltage be? Anybody have any thoughts? So I don't think it'll be -5 volts. So let's find out by doing Kirchhoff's voltage law around this loop, right? So we would have -5 volts, right? Which means +5 volts plus VD plus Vref, which in this case is 2 volts, is equal to 0. So we have 7 volts plus VD is equal to 0. What's VD? Negative 7 volts. Okay, so our VD is negative 7 volts for this case right here. Our open loop gain is 10 to the 5, so that means that we would have supposedly negative 700,000 volts. We know that's not actually true, right? And then that negative 700,000 volts would essentially be split between R out and RL. Since R out is so much greater than RL, we know that the voltage drop across RL will be approximately negative 700,000 volts, which would actually saturate to what? Oh, I didn't define VCC plus and VCC minus. So let's do that real quick. My apologies. So let's say that this guy is positive 10 volts and this guy is negative 10 volts. So if we mathematically calculated our output voltage to be approximately negative 700,000 volts, is that more negative than our supply voltage? You better believe it. So we should saturate to our negative supply voltage. So we should see that our output voltage is negative 10 volts. And I'm going to put a note here from saturation. Okay. Let's jump forward quite a bit, right? Let's see what's going on at positive 1 volt. Okay. So what should VD be at positive 1 volt? Negative 1 volt. So negative 1 volts times 100,000 would give us negative 100,000 volts. So the voltage drop across our load resistor will be approximately negative 100,000 volts. What would our actual output voltage be? Negative 10 volts again. So essentially what I've done here, and this is also due to saturation, is I've said that over the range, so if I put 2, 3, 4, 5. So here's negative 5 volts. Here's, actually, let me do it this way. So from negative 5 volts all the way out to 1 volt, our output voltage is saturated at VCC minus, where this line down here is going to correspond to negative 10 volts. And up here, this guy will be positive 10 volts, right? Let's look at what would happen if Vn were 1.99 volts. So what would our output voltage be in that case? Well, our differential voltage should be negative 0.01 volts, right? When we multiply that guy by 100,000, what are we going to get? Negative 1,000 volts. Still much greater than VCC minus. What if we made it negative, or excuse me, not negative, positive 1.999 volts? We're actually still going to wind up seeing that our output voltage should come out to be approximately negative 10 volts because of saturation, right? So in this case, our VD would be 10 to the minus 3, or 1,000th of a volt, or excuse me, negative 1,000th of a volt. We multiply that by 10 to the 5, and we get 100 volts. So as we get closer and closer and closer to 2 from the left, it's going to take us being only a few millivolts off before we actually, or excuse me, microvolts, until we actually start to see that we have linear amplification in this thing, okay? So at exactly 2 volts, what's VD? 0. So what's our output voltage? 0. And then let's look at 2.001 volts. Okay. So what's going on at 2.001 volts? What's our differential voltage? 0.001, so a thousandth of a volt or 1 millivolt. We multiply that by our gain of 100,000. And so we would have 100 volts. 100 volts is much larger than VCC plus, so we should saturate now at positive 10 volts. And as we continued on out to 5, it should be fairly obvious that we'll continue to saturate at 5 volts, or excuse me, at positive 10 volts. So our graph should look something like this. Oops, this should be red. So for all intents and purposes, any voltage less than our reference voltage, or excuse me, any input voltage less than our reference voltage is going to cause our output to saturate to the negative supply voltage, and any voltage greater than our reference voltage is going to cause our output to saturate to the positive supply voltage. So essentially, we can compare our input signal to that reference signal, and it's going to give us either a low voltage whenever we're below the reference signal, or a high voltage whenever we are above the reference signal. Now, I've drawn this graph as if the slope of the line around Vn is equal to 2 is infinite. That is not technically true. It is just incredibly steep because of the incredibly small linear range of the open loop amplifier configuration. So if we were to simulate this circuit and we zoomed in very, very close to 2 volts, we would see that it does actually have a finite slope. It's just going to be ridiculously large. Should be about 100,000 volts per volt. That's what the gain is literally doing. So in general, we can say that for a non-inverting comparator like this, our output voltage V out will be VCC plus whenever our input voltage is greater than our reference voltage, and it will be VCC minus whenever our input voltage is less than our reference voltage. So now I'd like to take a minute and show you how we could simulate this circuit. Let me know when you guys are ready for me to switch over to LT Spice. All right, let me find my cursor. So I'm going to make a new schematic diagram. And before I even bother with the op amps or anything like that, the first thing I'm going to do is actually set up all of my voltages, okay? So I like to do this in a way to where I essentially just apply nodal voltages to the different pins of my op amp so that I can keep my schematic clean. So I'm going to start by just dropping some voltage source here, V1, and I'm going to put another voltage source essentially below it like so. And I'm going to change the name of this guy from V1 to be VCC plus, just so that we know that this guy is what's going on with my positive supply voltage. And I'm going to change the name of this guy to VCC minus, just so that we know which role these guys are playing. For what it's worth, whenever I want to edit a text field, I just need to have my mouse on top of the text field and press right click. Now I'm going to wire these two guys together. And I'm going to put this middle point as my ground, like so. For the example that we just worked, VCC plus was positive 10 volts, VCC minus was negative 10 volts. I'm going to put that in as positive 10 because I have the positive polarity terminal of this VCC minus voltage source connected to ground. So the negative polarity terminal is going to be 10 volts lower than 0, or negative 10 volts. Another thing that I'm going to do, and you'll see why I'm doing this in a moment, is I'm going to label my network. So I'm going to have a VCC plus, and I'm going to tie that label to this positive polarity terminal node. And similarly, I'm going to have a VCC minus label down here. What this is going to allow me to do is essentially to reference these voltages elsewhere in my circuit. So instead of directly having to connect them to these pins of these voltage sources, I can just tell other parts of my circuit, hey, the voltage here is whatever voltage is at that node. And so it'll make things a little bit cleaner, as we'll see in a couple of minutes. Now I'm going to set up my reference voltage, which was just a simple DC voltage source. That should be a 2-volt source. I'm going to put ground at the bottom, and I'm just going to label this top node as VREF. And I'm going to give myself another voltage source. And this is going to be my input voltage. So I'm going to change its label to be VN. Once again, I'm going to put ground on the bottom. I'm going to label this guy as VN. And let's make this guy a sinusoidal voltage source, no offset. Let's make it have an amplitude of 5 volts so that it's oscillating from +5 down to -5. Just for the sake of argument, let's make the frequency 1 hertz so that it takes 1 second for it to complete that oscillation. And I want it to run for only 1 cycle. So I'm just going from +5 down to -5 and then back up to +5, and then it's turning off. All of that information will wind up showing up down here on our schematic diagram as well, unless you happen to check the box that tells it to not do that. But I always make sure to have that box checked so that you guys can see what the parameters are. Okay. So those are all of my voltage sources. Now I'm going to set up the op amp itself. Okay. So I'm going to go into my component thing, and I'm going to type in UNI. Okay. So we can see over here that there are several different universal op amps. Okay. These are all different than each other in slight ways. I usually use universal op amp 2 because universal op amp 2 gives me a slew rate limit, which we're not going to talk about much in this class. Slew rate is effectively just the amplifier's ability to process quickly changing signals without distortion. But it also gives me an output voltage limit, which means it's going to take into account saturation distortion effects. The higher level versions of the universal op amp also take into account higher level effects that we're not going to really bother with in this class. So universal op amp 2 is going to be kind of our sweet spot for a generic op amp. Okay. So I'm going to place this guy over here. Okay, so this is our universal op amp 2. Notice that it happens to put the non-inverting input terminal on bottom and the inverting input terminal on top. And then the supply voltages are exactly opposite that for some reason. So the positive supply voltage is on top, the negative supply voltage is on bottom. If we wanted to make it to where the inverting input terminal was on bottom, if I have this guy selected, if I press, I think it's Control E, it mirrors it, and then I can rotate it twice, and now the non-inverting input terminal is on top, the inverting input terminal is on bottom, but now our supply voltages are still swapped. There's no way to really fix that. So I used the move tool, which is M, and then I just dragged over it, and that allows me to pick up an element. In the older versions of LT Spice, there was a select tool, but that apparently has gone away. So I'm used to this too. Okay. Okay, so a couple of things that I'm going to do here just for the sake of argument. I'm going to give myself a little stub of wire here and a little stub of wire here and a little stub of wire here so that I can connect my resistors and things like that. So I'm going to put my 10 kilo ohm resistor down here. For what it's worth, if I were to right click on the op amp itself, most of these parameters are actually editable. So if I have, so right now it says my open loop voltage gain is 1 meg. So it means 1 million. I could change that to be 0.1 meg if I wanted to match exactly our parameters. I can change the rail to rail limit. So right now the rail to rail limit is 0 volts, meaning I will go all the way up to VCC plus and all the way down to VCC minus. We can change the input resistance. Right now it's at 500 mega ohms. I think I said ours was 1 mega ohm, so I'm just going to change that to 1 meg. There isn't a way to really change the output resistance. But you can change the limit on the current that can be output by the op amp, which is related to the output resistance. So, like I said, this guy will do most of the work that we need for this class pretty easily. I limit. Are you using Universal Op Amp 2? That's the problem. Universal Op Amp 2 is what we're using for our op amps. Yep. 0.1 meg, so that's 0.1 million, which is the same thing as 100,000. Realistically, it's going to make no difference to us whatsoever if you left everything at its default value. I just wanted to show you that you could edit the parameters with this particular op amp model if you were so inclined to do so. All right, so let me ground out the bottom of this 10 kilo ohm resistor. And now essentially I'm going to go through and label these things. So VCC plus, and I need to make sure that I use the exact same capitalization and all of that kind of stuff as I used over here. I'm going to drop down here. And so what that did is it's effectively applying the 10 volts that's at this node to the positive supply terminal of the op amp so that I don't have to run wires all over the place. I can make these guys look nice and neat. Similarly, I'll do a VCC minus, put it up here. I'll have a V in. So my input voltage should be on my non-inverting input terminal. My reference voltage should be on my inverting input terminal. And lastly, I'm just going to label my output voltage node here. Okay. And now I'm going to choose to do a transient simulation. And I'm going to run it for 1 second, which is just one cycle of the input. And run this simulation. Let me get this dumb thing out of my way. So the first thing that I'm going to do here, just for the sake of argument, is I'm going to plot my input voltage. So if I just mouse over this node that is at Vn and I click it, I have my nice sinusoidal input voltage that is going from positive 5 volts at its positive maximum to negative 5 volts at its negative maximum, which is exactly the range of voltages that we are concerned about, right? I constrained Vn to be between -5 and +5, and I have exactly that right here. I'm going to add to this simply my output voltage. Okay. So I just have my mouse over the V out node, and I'm going to left click. And what I see, what looks like what's happening, is that whenever my input voltage hits 2 volts or higher, my output voltage goes high. And whenever my input voltage is less than 2 volts, my output voltage goes low, exactly like what we expected, okay? Now we can actually generate, first before we go, can everybody see the blue and the green okay? Do I need to change the background from black or is that fine? Okay, everybody, nobody's saying change it, so I'm going to assume that you all can see it. Okay. So I can change my graph. Like right now, I have V in as a function of time and V out as a function of time. And while that's useful, I'm not really seeing V out as a function of V in, which would be more useful for this thing. So when I have my mouse over the horizontal axis and I right click, it says right now that my quantity plotted is time. I'm going to change that and I'm going to say plot against the voltage V in. And so I have two curves now. It's not super obvious, but this green curve is literally Vn versus Vn, or Vn as a function of Vn. So this is literally just a straight line with a slope of 1. That's not telling me remotely anything useful, so I'm just going to delete that guy. And what's left is my output voltage as a function of Vn. So I can see very explicitly that my output voltage is at negative 10 volts or VCC minus until I get to 2 volts. I hit my reference voltage, and then it shoots up to VCC plus, which is positive 10 volts, and it stays at VCC plus as long as Vn is greater than 10 volts. So I have exactly the response that I would expect that we got analytically through analyzing this guy. Okay. So this is a non-inverting comparator. If I were to swap the placement of Vn and Vref, what do you think would happen? Exactly right. So our graph should flip over so that I will have what's called a inverting comparator, okay? And so we can do that really easily by just deleting this guy and this guy, and then telling it, let's see, that I have my reference voltage. That's not how you spell reference. So if I put my reference voltage on the non-inverting side, and I put my input voltage on the inverting side, except that I missed, and I run my simulation, the graph swapped over. So essentially, whenever my input voltage is less than my reference voltage, now I get a high output. And whenever my input voltage is greater than my reference voltage, now I get a low output. And it's all because I've effectively swapped the sign on the VD from the previous example. Okay. So we'll more formally write that out here on our notes. Yes.
How do we change the graph? We changed our x-axis to be in terms of v.
Yes.
Okay. How do we do this?
Okay, so when I have my mouse over the x-axis and I right click, I can change where it says quantity plotted. By default, it is time. I am specifically telling it plot as my input the voltage. So that's what that V open parentheses is saying. It's going to be a voltage. And then that V in is the voltage at the node I've labeled V in. So that's how I'm plotting it as my input voltage as my x-axis, and my output is still the out, or the y-axis. Okay. All right. So let's talk more formally then about the inverting comparator. Okay, we won't go through as much rigor of mapping everything out here because I don't think it's particularly useful. So our inverting comparator circuit is literally the exact same thing as we had for our non-inverting comparator, except that we swap the position of Vn and V reference, right? So on my non-inverting terminal, I'll have my reference voltage. On my inverting input terminal, I'll have my input voltage. Here's my load resistor RL, my output voltage V out, VCC plus, and VCC minus. And for what it's worth, our plot for this guy, as we saw a moment ago on LT Spice, should look something like this. So we should be staying high until we hit VREF, at which point we should switch over and stay low. So this is literally the exact same graph as we had previously, except that it's just flipped upside down, right? Where this guy corresponds to a voltage of -10, this guy corresponds to a voltage of +10. So that we can say, in general, our output voltage for this case is going to be VCC plus whenever Vn is less than Vref, and it'll be VCC minus whenever Vn is greater than Vref. All right. So how are you guys feeling about the non-inverting and inverting comparator circuits? Okay. Anything particularly confusing? Let's start there. So what I want us to do is to design something, okay? So this is the third day of class and we're going to design something already. Yeah, absolutely. So design example number 1. So I want us to design a 1-bit analog to digital converter such that V out is equal to 5 volts when V in is greater than 3 volts and V out is equal to 0 volts. So I'm having a digital high of 5 volts and a digital low of 0 volts when V in is less than 3 volts. So this is our first design project. Okay. So we've learned of a whopping 2 circuits to this point. So you have a 50-50 shot of just blindly guessing this and being correct. Do you think we should implement this circuit using an inverting comparator or a non-inverting comparator? A non-inverting comparator, because we want our output to go high when our input is higher than our reference circuit. Okay, so we're going to be dealing with a non-inverting comparator. So let's just start with the basics here. So for a non-inverting comparator, my input is applied at the non-inverting input terminal, and my reference is applied at the inverting input terminal. I'm going to take my output at the output terminal, fairly obviously. So what are my supply voltages going to be? Let's start with VCC plus. 5 volts, because we want our output to be 5 volts when our signal is high. We need to put 5 volts on the positive supply side. What about our VCC minus? 0. So we're just going to ground that side. Okay. So we have a simple ADC. Okay. We could throw this into LT Spice if we were so inclined. Wouldn't be particularly difficult to edit what we've already got. But let's think about this and see if we can do a little bit better of a job. So let me explain what I mean specifically by that. The way that we have this circuit currently implemented, it would require a 5-volt source and a 2-volt source. It's not really tenable in a practical sense for us to have multiple voltage sources for this thing to work. So it might be better if we can figure out how to use that 5 volts to make our reference signal from that using some sort of network. Anybody have any idea how we might be able to step down 5 volts to 3 volts like we need here? So not a transformer. I mean, that's definite. Well, this is DC, so transformer wouldn't even work. What did you say? So we're not going to use a resistor, but we are going to use a resistive divider, more commonly known as a voltage divider network, in order to facilitate this. So I might expand this guy a little bit. So those are still going to be at 5 volts and ground. But what I'm going to do is I'm going to essentially give myself access to like a 5-volt supply rail and a 0-volt supply rail, or to put it more bluntly, just a common ground rail down here. And I'm going to erase that V reference thing. And what I'm going to do is I'm going to try to come up with some sort of voltage divider network that will allow me access to 3 volts. So my question to you all is, what values of resistors should I use to make that happen? Anybody have any thoughts? So to be clear, essentially what we're doing, I'll do it over here in blue because this is technically an aside, is we've got 5 volts up here. We have some resistor R1, some resistor R2, and we want the voltage at this node, which is the same thing as the voltage drop across resistor R2, to be 3 volts. And we're trying to decide what R1 and R2 should be. That is 100% what's going on here, yes. So if we use the voltage division equation, sorry, I didn't mean to do that, we would know that this 3 volts is equal to 5 volts times R2 over R1 plus R2, right? That's simple voltage division from obviously circuits 1, but even way back in engineering 120, you guys were doing this. Whether or not you realize it is another bag of cats, okay? So still waiting for numbers from you guys.
3 and 2.
So 3 and 2, absolutely. So which one is 3?
Or no, R2.
So R2 would be 3 and R1 would be 2. So that would give us 5 times 3 over 5 is 3. Absolutely. Now, we have to pay attention to the size of the resistors that we are going to use here, because the internal input resistance of our op amp is on the order of mega ohms. If I chose R1 to be 2 mega ohms and R2 to be 3 mega ohms, I would see that a comparable amount of current that's flowing through R1 would actually flow into the input terminal of our op amp, and my voltage would not be the 3 volts that I'm expecting. And I'll show you that in a moment. So realistically, we need to choose our resistor values in a practical sense to be much smaller than the internal input resistance of the op amp, so that we ensure that practically no current will flow into that input terminal and mess up our voltage division ratio. So the kilo ohm size resistor is usually the sweet spot for biasing op amp circuits, because it's about 1,000 times smaller than the input resistance of an op amp, and it's about 1,000 times larger than the output resistance of an op amp, so that if we use kilo ohm size resistors for any well-designed op amp, we will always be okay, because we know that our voltage divider at our output will always be treating that R out as effectively 0, and our input resistance will always be so much larger than our resistors, our biasing resistors, no current will flow into the input terminals. So I would choose here a 2 kilo ohm resistor and a 3 kilo ohm resistor, like so. So let's implement this circuit in LT Spice. So I'm going to get rid of this guy for now. So as far as my supply voltages and all that kind of stuff is concerned, I'm just going to make this guy 5 volts, this guy 0 volts, although realistically I could just put it as ground and it isn't even necessary. My reference voltage should be, actually I'm not going to use a reference voltage anymore, so I'm just going to delete that guy. Piece of crap. So let's see, let's delete this and this and this and this and that. And I'm just going to move this transient thing just out of the way over here for now. I'm just going to give myself a section of wire up here for my positive supply bus. And I'm going to give myself a section of wire down here for my negative supply bus. I'm just going to label this guy VCC plus. And I'm going to label the one on bottom as VCC minus. Round that guy out. And I'm going to put 2 resistors in series. There's R2. I'm going to make this guy's name be R1 in just a second by making this guy's name change to RL. So we said that this guy was a 2 kilo ohm resistor. This guy was a 3 kilo ohm resistor. And the last thing that I need to do, oh, I need to wire up my supplies. Is put in VN. Actually, sorry. That's not going to work here. Sorry about that. Because the supply terminals are on the opposite side. So I'm still just going to label those guys. Just for whatever reason, when they designed the op-amp schematic symbol, they put the positive supply voltage on the inverting input side. Actually, I know exactly why they did that, because the overwhelming majority of the times you're using op-amps as negative feedback circuits, and it's more convenient to put the inverting input terminal on top. But anyway. All right, so here is our circuit. Let's simulate it. And let's look at our input signal. And then also our output signal. And it looks like now our output is going to 5 volts whenever our input is equal to or greater than 3. And then our output goes to our digital low whenever our input voltage is less than 3. And we can obviously look at that by plotting our output as a function of Vn again. And just for the hell of it, just so that we can see, might make that a bit better. Yeah. So whenever our input voltage is less than 3 volts, our output is low. Whenever our input voltage is greater than 3 volts, our output is high. Exactly what our design constraint was. If we look on our schematic diagram and I mouse over that node, we can see that the voltage there, it isn't exactly 3 because we're dealing with a real op amp, so there will be some small amount of current that flows into that input terminal. But we can see that the voltage at this node is 2.9994006. So it isn't exactly 3, but it's pretty damn close. If I were to change this from 2 kiloohms to 2 mega ohms, and from 3 kiloohms to 3 mega ohms, and I rerun my simulation, now I see that my transition from low to high actually occurs a little bit below 3 volts. And when I mouse over, it's because the reference voltage that we are referring to is 2.727 repeating, because we are having current leave that node and flow, or an appreciable amount of current is flowing through that resistor R1, and then some of it is being bled off and flowing into the input terminal of the resistance, or excuse me, of the op amp. Okay. So that's why that kiloohm size of resistor is really the sweet spot for op amp biasing. Okay. So the last thing that I want to do is show you one of the drawbacks of comparator circuits. Okay. So what I'm going to do is I'm going to put another voltage source on top of this input voltage. And this second voltage source is meant to introduce some noise into our system. Okay. So actually, I don't want that voltage source. I'm going to go to components, and I'm going to do BV. So this is a behavioral voltage source. That's just a fancy word for effectively dependent voltage source in LT Spice speak. And what it allows me to do is it's going to generate a voltage that is a function of something. Okay. So I'm going to put these two guys in series so that my new input signal, I'm going to call this at this top node Vn, excuse me, Vn plus N for Vn plus noise. Delete that guy. And now I'm just going to edit this guy. And I'm going to say that my voltage that's being provided by this extra source is going to be white noise. And you can change different parameters for white noise. You guys don't literally ever have to do this. I'm just trying to show you something interesting. So I'm going to have a white noise voltage generator added onto my simple input sinusoid. I'm going to run my simulation. And if I click on this VN plus noise, you can see that it's not a pure sinusoid anymore. There's a little bit of noise added on top. Well, when I look at my output voltage, that's not as gross as I want it to be. There we go. Now it's real gross. Okay. So the size of that noise ripple is only on the order of probably 100 millivolts, right? What's going on in this region right here and this region over here?
Is it dropping really fast between 0 and 5 volts multiple times?
So it is. So every time, so because my comparator circuits are so sensitive, because we have that open loop gain that is really, really high, anytime my voltage is even slightly over my reference voltage, it's going to swing up to VCC plus. And anytime it's slightly below my reference voltage, it's going to swing down to VCC minus. So if I have a noisy input signal like this, I'm going to see effectively ringing between my output voltage is going to swing between VCC plus and VCC minus until my input signal is consistently either above my reference voltage or below my reference voltage. So the first circuit that we're going to look at on Wednesday's class is actually going to use positive feedback and latching to get rid of these noise problems. So when you guys, if you ever buy an off-the-shelf comparator circuit, it will actually have some built-in latching, which is what we're going to be talking about in our next class meeting, so that you don't have to worry about this. So real practical comparators that you buy off the shelf takes care of this noise problem for you. But if your noise is large enough, you would have to use the things that we're going to talk about on Wednesday in order to fix them. All right, I think that's enough out of me for today. So we're getting out about 15 minutes early.